Hello, my name is Farah Izzati binti Syafi'i, a group leader from Group 17. Here I am with my other members, which is Genevieve Kurin, Harry Popop Simon, Muhammad Daniel Fakri bin Yaakob, and Siti Rozila binti Muhammad Zain. Will present our project on modeling Covid-19 outbreaks in Malaysia using a system of differential equation.
Hello, my name is Muhammad Daniel Fakri bin Yaakob. So, for introduction part, SARS-CoV-2 or as known as COVID-19 has been discovered as the source of a severe acute respiratory disease that has spread throughout the world. Malaysia government, through the Ministry of Health, has developed a focused testing strategy to make the best use of country-limited medical resources in combating the COVID-19 epidemics. To model COVID-19 transmission dynamic in Malaysia and its combined influence with limited medical resources and false detection problem, we utilize a simple epidemiological system which is SRS type system.
Hello, it's me again, Farah. So in this slide, we will need to model the combined effect of limited medical resources in COVID-19 pandemic. So this is the general epidemic or SIR model. We divide the population into three groups, which is S for susceptible class, I for infective class, and R for recovered class. So the equation will be like these three equations. For the standard SIR model, we assume that the population size is large and constant, which S plus I plus R will be equal to N, where N is the populations of individuals. In this model, there are no birth and no death, or also no immigration or emigration. And also there are no latent period, or we call it as a quarantine period, where the time of the infection will not show any symptom. This model is homogeneous mixing, and the infection rate is proportional to the fraction of infective, which is lambda equal to beta I over n, and the recovery rate is constant, which is gamma. From the general basic SIR model that have been shown before, we may extend it to three kinds of model by considering the different parameters. For the second model, we extend the SIR model with demographic term, which is in birth and death rate. The terms mu and v indicates the birth and death rate respectively. So the model will extend like these three equations, where we add the mu and v term. The blue arrow here indicate that the birth rate at susceptible, and the red arrow here indicate that the death rate, which the individual population we divide into three groups. Each group in this population will be died. So in this equation, we will have new term, which is mu and v. In this model, we assume that all the individuals experience the same background of mortality, and the newborn will enter the susceptible class. For the third model, we extend from the previous model with new term, which is we add the reinfection rate, which means we assume the recovered population will enter the susceptible and it will be potential to be infected again. So the epsilon here indicates the transfer rate from recovered to susceptible. So from the previous equation, we will add new term in this three equation, which is epsilon. This model is called SIRS model. In this context, the individual recover from the COVID-19 will have the immunity against the virus, but the immunity will wear off and they eventually become susceptible individuals to the virus. And for the last model is extend from the previous SIRS model, we consider the efficiency of the medical resources supply. In this model, we include the term alpha I over omega plus I, which will measure the limited medical resources being distributed. Alpha is the medical resources supply per unit time. I is the infected population and omega is the efficiency of the medical resources supplied. The lower the value of omega, the higher the efficiency of the medical resources supplied. So this is the three parameters of SIRS model in cooperating reinfection and medical resources scenario. This is the reverse process that we obtained from the model 4 to model 3, 2 and model 1, which is the basic SIR model.
Hello Dr. Hafiz, my name is Harry Popov Simon and I will continue the presentation on the steady states. So as presented by Farah just now, we have three extended models and here we will find the steady states for each model using Mathematica software. Now let's look at the steady states obtained by using Mathematica software for the second extended SIR model with demographic terms or the birth and death rates. Here is the coding in Mathematica software to find the steady states for extended model 2. Based on the outputs from Mathematica, we found that there are two types of steady states, which are disease-free equilibrium and endemic equilibrium. The reason why the first steady state is of the type disease-free is because the component I is equals to 0. The endemic type steady state are in a general form with many parameters. Next is we will find the steady states for the extended model 3, which is the SIRS model that is with reinfection term. So this slide shows the coding in Mathematica software to find the steady states for extended model 3. Based on the outputs from Mathematica, we found that there are two types of steady states, which are disease-free equilibrium and endemic equilibrium. And notice that the disease-free steady state for this model 3 is the same as in model 2, whereas here the endemic type steady state are with more parameters. We will also find the steady state for the fourth extended model, which is the SIRS model with epidemiological factors on limited medical resources. This slide shows the coding in Mathematica to find steady states for extended model 4, and the highlighted in blue is the disease-free steady state because, as mentioned, the component I is equivalent to 0. And we can also see part of the solution for S of the second steady state. This slide shows the continuation of S for the second steady state of the type endemic. This is the final continuation of S for the second steady state of the type endemic. This slide shows the calculation for value of I for the second steady state of the type endemic. This is the highlighted calculation for value of R for the second steady state of the type endemic. This is the continuation of R of the second steady state. This is the final continuation of R for the second steady state. So this is the value of S for the third steady state of the type endemic. This slide is the continuation of S for the third steady state. This is the continuation of S for the third steady state. This slide is the final continuation of S for the third steady state. This slide shows the value of I for the third steady state of the type endemic. So this slide consists of the continuation of I for the third steady state and the value of R for the third steady state of the type endemic. Continuation of R for the third steady state. Continuation of R for the third steady state. These are the steady states obtained for the fourth extended model. The first steady state obtained is mu n over v 0, 0, and it is a disease-free equilibrium type. Just like the previous steady states, from second and third extended model. Meanwhile, the other two steady states can be deduced to S asterisk, I asterisk, and R asterisk. This is because the solutions for these steady states are very lengthy and convoluted, making it difficult to solve.
Assalamualaikum warahmatullahi wabarakatuh. My name is Siti Rozila binti Muhammad Zain with matric number 146560. So in this slide, I would like to proceed with the topic of stability analysis. In this project, we will only consider the disease from steady states for all the three extended models. This is because, as we have seen in the previous part, the endemic steady states are very complex where it contains all the variables and in the general form. Also, it is because we want to see when an outbreak starts or eliminated, that is, the disease-free steady state changes stability from stable to unstable or vice versa, and similarly, the endemic steady state gains or loses stability. For the extended model 2, this is the 3 by 3 Jacobian matrix. Now we proceed to find the eigenvalues by solving the characteristic equations J minus lambda I by using Mathematica software, and the highlighted part is the eigenvalue obtained. Since we have the case of repeating eigenvalues in this extended model 2, then it is easier if we interpret the stability of the steady states by some values for the eigenvalue. So we use the fitted parameter values from article 1 to substitute into the eigenvalues equations. Then in this slide, we calculate the eigenvalue using eigenvalues equations. Then we obtain the eigenvalue 1 is equal to eigenvalue 2, which is negative 0.00002, and for the eigenvalue 3 we got 1.0198. Since they are of the opposite sign, then we can conclude that the disease-free steady state for this extended model 2 is not stable, which means we will not observe the disease-free steady state in our real situations. For the extended model 3, this is the 3 by 3 Jacobian matrix. Now, we proceed for extended model 3 to find the eigenvalue using Mathematica, and the highlighted part is the output of eigenvalues. For the model 3, we also found that this eigenvalue is stable. Since all the parameters are positive, then the disease-free steady state is stable when eigenvalue 3 is less than 0 as well. Because when we know that all the three eigenvalues are real and unequal, so the only way for the steady state to be stable is that we can make all the three eigenvalues are of the same signs, which is negative signs. And for the extended model 4, this is the 3 by 3 Jacobian matrix. Then we proceed with extended model 4 to find the eigenvalues using Mathematica, and the highlighted part is the output of eigenvalues. We found that the eigenvalues 1 and eigenvalue 2 are less than 0. So, since all the parameters are positive, then the only way for the disease-free steady state to be stable is when the eigenvalue 3 also smaller than 0, because we know that all the three eigenvalues are real and unequal. So in this slide, the thing that you need to know is the use of basic reproduction number, where it is to quantify the severity of transmission of disease. It is an epidemiologic metric that used to describe the contagiousness of disease. So there are three different conditions of basic reproduction number that you need to know. Firstly is when if R naught is less than 1, the disease will not spread and it will eventually die out. Second, If R0 is equal to 1, the disease will remain stable in the community, but epidemic will not occur. And the last condition is when R0 is larger than 1, the disease will spread and epidemic may occur. For extended model 4, it is the basic reproduction number is indicated as R0 L for epsilon larger than 0 and alpha larger than 0. Whereas for extended model 3 and model 2, their basic reproduction number is indicated as R0 U for epsilon larger than 0 and alpha and omega is equal to 0. For the model 1, which is the simplest SIR model, it is the basic reproduction number is indicated as R0 S, and this is at the outset of epidemic, where nearly everyone is susceptible. For the simplest SIR model, which is the model 1, we will focus on the second ordinary differential equation, which is di over dt is equal to b times I times s over n minus gamma times I. At the outset of epidemic, nearly everyone is susceptible, so the susceptible can be approximated by n. Hence, we get di over dt is also approximately in the bracket of beta minus gamma times with I. And if the beta minus gamma is larger than 0, the infected individuals will increase over time. For the next slide, we will see how the basic reproduction number is defined. So first, if R0 S is larger than 1, the infected individuals will increase over time and the epidemic will occur. But if R0 is smaller than 1, the infected individuals will reduce over time and the epidemic is eradicated or will not occur. So here is how we obtain the basic reproduction number shown in previous slide. The basic reproduction number is obtained by Eigenvalues analysis using Eigenvalue 3, where we said Eigenvalue 3 is larger than 0 and Eigenvalue 3 is smaller than 0. For extended model 2 and for extended model 3, they have the same form of the third eigenvalues. That is why they have the same form of basic reproduction number as well. And recall that when eigenvalue 3 is smaller than 0, it gives us a stable disease-free steady state, and from here also we can see eigenvalue 3 is smaller than 0 will lead to reproduction number smaller than 1. This means that there will be no epidemic. On the other hand, for eigenvalue 3 is larger than 0, it will give us an unstable disease-free steady state. Then from here, we can also see that the reproduction number is larger than 1, which means the epidemic will occur. Then for extended model 4, similarly, we use method of eigenvalue analysis to obtain the basic reproduction number. And recall that when eigenvalue 3 is smaller than 0, it gives us a stable disease-free steady state, and from here also we can see the eigenvalue 3 is smaller than 0 will lead to reproduction number is smaller than 1. This means that there will be no epidemic occur. On the other hand, for eigenvalue 3 is larger than 0, it will give us unstable disease-free steady state. Then from here, we can see that it's follow that the reproduction number is larger than 1, which means the epidemic will occur.
Hello, my name is Genevieve Kurin. I will present the numerical findings of this project. Firstly, we will do numerical analysis for extended model 3, the SIRS model with reinfection term. This is the coding in the notepad before we run in the XPP-Auth software. All these parameter values are obtained from the fitted parameter values in research article 1, and the initial value of n will let it be 6800, and the initial values of s, I, and r are also let it be as follows. This is page 3 of research article 1, whereby we take the fitted parameter values from here for the coding in Notepad. Beta equals to 0.16, gamma equals to 0.058, mu and v equals to 0.00002, epsilon equals to 0.0009. So this is the figure obtained from XPP-Auth software. And at the early stages, we can see that before plus minus 900 day, the infected cases are approaching zero because the patient may be immune to the coronavirus after they have recovered. This explains why the susceptible individuals are increasing. At the same time, the recovered individuals are decreasing, because as we have assumed in the SIRS model, those who are removed from the recovered class will re-enter the susceptible class and have the potential to be reinfected. Since there are potential for reinfection to occur, we can see that there are infected cases again around the 1000 day, and this pattern continues, which means that the epidemic persists. The epidemic will persist until the curves are flattened. Or in other words, the epidemic persists until we achieve the stable, disease-free steady states. And from the fitted parameter values in research article 1, we can calculate the basic reproduction number R0U as 2.7577. This means that one infected person can infect average 2 to 3 other people. Next, we do numerical analysis for extended model 4, the SIRS model incorporating reinfection and medical resources scenario, whereby alpha greater than 0, epsilon greater than 0. This is the coding in the notepad, and as highlighted in blue color, we let alpha equals to 1 and let omega equals to 0.1. So from this figure generated from XPP-Auth software as well, we can see that the cases of infected individuals are approaching zero, and no reoccurrence of infected case within 4,500 days. This is because we have medical resources supplied at alpha equals to 1 with its efficiency omega equals to 0.1. Hence, infected patients are getting very efficient medical resources. We can say very efficient because the values of omega is quite low. It is 0.1. Hence, this makes them recover faster. In other words, the curves achieve stable, disease-free, steady states faster as well. Also, we can see that the recovered curves are approaching zero as well, because there are almost no infected cases already. And And as we have assumed in the model, those who are removed from recovered class will re-enter the susceptible class. This explains why the susceptible curve are approaching the total population n equals to 6,800. To analyze further, we increase the value of omega to 80, as highlighted in blue color. So this is the figure when we increase the value of omega. The value of omega here equals to 80, while we maintain the alpha equals to 1. This means that there are lower efficiency of medical resources supplied. Hence, when there are lower efficiency of medical resources, the epidemic will occur in the long run, as we can see in this figure. It is hard for the curves to get flattened as time increases, whereby here, within the 100,000 days, there are resurgence in the COVID-19 cases. There are no curves that are plateauing.
Hello, it's me again, Daniel. So, for the part opinion of government effort in combating COVID-19 outbreak. First, based on the numerical finding of the COVID-19 cases from 24th of March to 23rd of April 2020, it is observed that the daily cases recorded is reduced to a small number. This is illustrated in X-bar graph that the curve for the infected individuals show to be flattened. The government effort, such as the implementation of Movement Control Order (MCO) on 18th of March 2020, is the main factor that contribute to this reduction of infected individuals along the favored time. Other than that, the transmission dynamic of COVID-19 also depend on the value of recovery rate, which is gamma, and the medical resources per unit time, which is alpha. The value of alpha and gamma is directly proportional to the number of R, which is the recovered class. According to the ministry data, about 4,599 beds were accommodated for COVID-19 patients at about 40 hospitals. It also equipped with a combined 1,090 ventilators provided by the Ministry of Health. Theoretically, when the number of medical resources increase, the number of recovered individuals should also be increased. Therefore, the effort by the government to improve the medical facility also contribute to the reduction of daily COVID-19 cases. It was observed to be true in the day forward after 23rd of April. Issue of moral decision making in adapting to COVID-19 pandemic. The public need to have a proper knowledge about the virus and understand the impact that it can bring to humans. The government should always be prepared for unprecedented events. In this scenario, they should improve the medical facility and ensure to have a sufficient medical resource. Lesson learned from the modeling exercises. According to this modeling, the addition of the factor reinfection and false detection give more realistic prediction. Other factors, such as alternative stable state phenomenon, can interfere with distinct epidemiological forces and lead to catastrophic in transmission dynamics. The movement control order, quarantine and social distancing to be further practiced so as to break the chain of infection and flatten the infection curve. This group project has opened our eyes to the vast uses of mathematics in our daily life. That's all from us. Thank you.